So the thing that we've been doing in this section and the last one is something that's actually a special case of what's called a Riemann sum. It's spelled Riemann, and it's pronounced Riemann. And what Riemann sum refers to, just at a very high level, is whenever we talk about choosing rectangles that can approximate the area under some curve, we're doing a Riemann sum. Um, the fact is there are generalizations of this. We've written out the formula in summation form for a Riemann sum that has two specific limitations. One is that the intervals are all the same width. We take the full interval AB divided by n and get a whole bunch of intervals that are all the same width. In theory, we don't have to do this. In theory, we could choose a bunch of intervals that were of different lengths as long as together they made up the whole interval. We're not going to use that generalization in this course. The other generalization is that technically we can pick the height of the rectangle from anywhere in the interval. It doesn't have to be the right endpoint or the left endpoint or the highest or lowest point in the interval or the midpoint. It can just be any point in the subinterval and it would still be a Riemann sum. So that's why we're talking about a very specific case of a Riemann sum. But in general, you should associate the phrase Riemann sum of f of x on the interval AB with n subintervals with this concept of a whole bunch of rectangles that are chosen in the way we've been talking about to approximate the area under a curve. You noted that you need four things really. You need a function, you need a left and right endpoint, those are two of the things, and you need n, the number of subintervals, in order to be able to talk about a Riemann sum. Now, the idea behind defining this special Riemann sum in the situation where there are n subintervals is that the more subintervals that I have, the more accurate the approximation of area gets. So it's not much of a stretch of the imagination to say that if four rectangles gives a good approximation, and let's say 100 rectangles gives a better approximation, then what if we had infinity rectangles? Wouldn't that give the exact area under the curve? So I want to show you how we do that. Is basically what we do is we put together this notion of a Riemann sum, this approximation of rectangles, and the problem that we just did previously in the previous video segment, where we found the limit of a Riemann sum and the limit of a Riemann sum and a factor of 1 over n squared. And we're going to put that together and use that combination of skills to be able to find the exact area under a curve. Now, I know that some of you have already taken a calculus course. You know that there is a formula for finding the area under a curve. I promise we're going to get there, and this is how we're going to get there. We're not there yet. So as far as we're concerned at this point, if you know about the formula for an area under a curve, you actually don't know it. Just pretend you don't know it, and just bear with me while I explain this. So what we're going to do is we're going to use the limit of a right endpoint Riemann sum to find the exact area under f of x equals x squared on the interval 0, 1. And I've just put up here again that formula for the right endpoint equal length interval Riemann sum, which I've been calling the area approximation. We now know the term for this is it's a special kind of Riemann sum. Okay, so what I want to do is I want to be able to find this area. Here's the parabola y equals x squared. We've got the interval 0, 1. And what I want to be able to do is find the exact amount of this area. So what I'm going to do is I'm going to write out the formula for a Riemann sum. And just as I talked about a few minutes ago, what I'm going to do is I'm going to let the number of rectangles become infinite, so that if a lot of rectangles gives a good approximation, infinity rectangles gives an exact approximation. That's not really a term. The point is it gives the exact area. So let's write out the formula for the right endpoint approximation, or the right endpoint Riemann sum with n rectangles. We need, in order to apply this formula, we need to know what f is, what a is, and b is. So we can write that out. We see that f of x is just given in the problem. It's just x squared. A is equal to the beginning of the interval, which is 0. B is equal to 1. We therefore see that b minus a is equal to 1 minus 0, or 1, because we're going to need that in order to apply the formula. So we can see that the area is approximately equal to the sum from k equals 1 to n of, I have 0 plus k times 1 over n times 1 over n, which I can rewrite as sum from k equals 1 to n of, oh sorry, this is squared because I'm actually, the function is x squared. So since I'm taking f of 0 plus k times 1 over n, as you can see here, and applying f to that, I have to square what goes inside. So I'm rewriting this as k over n squared times 1 over n. So just to be clear, this is f of a plus k b minus a over n, and then this is b minus a over n, right there like that. Okay, so this is the formula for the area approximation using n rectangles. What I want to do is find the limit of this expression as n approaches infinity, because that's the closest I can get to using infinity rectangles. I can't actually just plug in infinity, but I can find the limit as n approaches infinity. So let's do the area equals, I no longer have to put an approximation here because I'm going to find the exact area. This is going to be the limit as n approaches infinity of the sum from k equals 1 to n of k over n squared times 1 over n. Now, I'm going to do some simplifications here. This is going to be the sum from k equals 1 to n of, I want this to be written as k squared over n squared times 1 over n, like that, because now I can simplify this as the sum from k equals 1 to n of k squared over n cubed, like that. So let us pull out the n's, the 1 over n cubed. And 1 over n cubed is not, this is not part of the summation. The summation only involves k, so the n, which is just, it happens to be the upper limit, but that's sort of irrelevant. This n doesn't change no matter how many terms of k equals 1, k equals 2, k equals 3. The n is going to stay the same. So I can pull it out and write the limit as n approaches infinity of 1 over n cubed times the sum from k equals 1 to n of k squared. So now we're going to use the formula that we know for the sum of the first n squares. So that's going to be the limit as n approaches infinity of 1 over n cubed times that formula, which gives n plus 1, 2n plus 1 over 6. Right? In other words, I just replaced that summation with this. And now I just have a simplification that I can do using what we already know about how to evaluate limits. This is going to be, let's see, that's going to be 2n cubed. I'm going to do this in my head, so that's going to be n, 2n, that's 3n, plus 3n squared plus n over 6n cubed. And I'm going to multiply this by 1 over n cubed over 1 over n cubed. That gives me the limit as n approaches infinity, make that infinity a little nicer, n approaches infinity of 2 plus 3n squared over n cubed is 3 over n, plus n over n cubed is 1 over n squared, and then on the bottom we have a 6. So substituting in, we get 2 plus 0 over 6, which is just 2 over 6, or 1/3. So that's the exact area. That's the exact area under the curve like that. So once again, I know that many of you know how to do this with antiderivatives because you've taken a calculus course. For this section, you can't do that yet. We'll get to that, but for now, you have to understand how to find this area by this method, by setting up the correct Riemann sum for n rectangles and then finding its limit using summation formulas.